Hello everyone, Assalamu alaikum. Welcome back. In this video, I am going to show you how we can implement a Perceptron in Python using Numpy and PyTorch. So I will be using Jupyter notebooks because I think for simpler code examples, it's actually quite nice to use Jupyter notebooks because I can execute one thing at a time and it will make things easier to explain. However, later on we have to move on to Python script files because when the deep learning models become larger and larger, managing them in Jupyter notebooks can be a little bit tedious and also dangerous. Well, because it's easy to lose the overview and debugging is a little harder if you have separate cells and stuff like that. And then the danger is that you might execute things out of order, and also you want to import certain aspects from different files. You don't want to have everything in one notebook because then it becomes really confusing and unmanageable, but we will get to these parts later on. So back to this topic of perceptron implementation in numpy and pytorch. Let me now walk through my numpy notebook. Now the PyTorch notebook is actually very similar, which is one of the cool things about PyTorch because it is very similar to NumPy, except there are some extra features that we will be using later on, and I will have a lecture on PyTorch where I will explain you these differences. So for right now, it doesn't make such a big difference whether we use NumPy or PyTorch notebook. I will also show you a step-by-step comparison after I explain the NumPy notebook. So you will see that's actually difference between the two. But let's do one thing at a time, right? All right, let's include some headings and then we will get on with the code. So I'm importing some libraries for those who do not use those who have not used notebooks. This one here, this command is for showing plots in the notebook. It's technically not necessary anymore, but sometimes on some computers plots will not be shown in a notebook if you don't include this line, and it doesn't hurt to include that line, so I always do this. Okay, so I've typed some code. Now let's just try to understand this and then we will move on. So here I'm just loading the dataset. So there is nothing really interesting happening here, but I will go through this step by step. So the data set is like some toy data that I generated. Let me show you how that looks like. So here I have two feature columns. I didn't include any column header, but this is the first feature, this is the second feature value, and this is the class label here. So there are zeros and ones, and you can see the dataset is not shuffled. And actually it's helpful for learning if the dataset is shuffled. It will make the learning a little bit faster in Perceptron. So here I'm loading the data into Numpy. I can also use pandas, but I thought it might be overkill because it's a relatively simple dataset. And then I'm assigning the features to X, which is a matrix, and then Y, which is a class label. I can maybe show you just how they look like. So typing this, and so this is X, it's a matrix, and then this is Y, which is a class level array. So here it's shuffled because I actually executed this whole bunch of code. So you can then already guess what's going on here. So here I'm loading the data and then just printing some summary information. It's always, I think, a good idea to do that to get an idea of things. So we have 50 labels from class 0 and 50 labels from class 1. We have this 100 data points in total and 2 feature columns and also 100 labels. So for example, here we can see these and these match, these numbers match. So and that's why what we expect. Then here I'm shuffling the dataset so that they are not all in order, they are shuffled. And how I'm doing that is I have to shuffle X and Y together, right? So everything otherwise will be mixed up. Then the features won't correspond to the class labels anymore. So how am I doing that is I'm creating the shuffle index. So I can just show you creating this shuffle index here, and how it looks like. This is just numbers from 0 to 99, so the 100 indices, and then I'm actually shuffling these indices. So here I'm generating a random number generator, and I'm shuffling these indices here. So you can look at these after shuffling. So after I execute that, you will see that they are now in random order. And then I'm using that to select the data points from X to Y, from X and Y, and then X and Y will be shuffled based on the shuffle index here. So that's how we shuffle. And then I will use the first 70 data points for training and the last 30. So we have these 100 data points from 70 to 100. The last 30 data points will be for our test set. Later on, we will be seeing or using more convenient ways to load data in PyTorch. So there are some loading utilities here. I'm just doing it step by step, so you get a feeling of what's basically going on. And then I'm normalizing the data. So this is sometimes also called standardization. Here I'm standardizing the data such that after standardization it will have mean 0 and unit variance. So I'm subtracting the mean and dividing by the standard deviation. So here I'm computing the mean and standard deviation of my sample, and then I'm subtracting the mean and dividing by standard deviation, and then both will be having mean 0 and standard deviation 1, so unit variance. So you can actually check that. Okay, very close to 0. So this is 17 digits after 0, so 0.000 or something up to 2. It's very small. It's almost identical to 0 essentially. And then for the standard deviation it should be around 1. So yeah, it is around 1. So the data is standardized. Well, why am I doing that? It kind of speeds up training a little bit. It's like stabilizing the training for Perceptron. It's not that necessary, but it is a good practice to do that for other types of optimization algorithms later on when we talk about stochastic gradient descent. So this is something like standardization that is usually recommended. The only types of machine learning models where this is really not that necessary is for tree based models. But all other machine learning deep learning models, I know they usually can benefit from that. especially stochastic gradient descent, will just learn faster. Okay, now let's take a look at our data. Now let me write some code for that. So here, this is our training set, how it looks like. You can see it's around centered at 0. We have two classes, class 0, these circles here, and then the square for class 1. So feature 1 and feature 2, that's our training set. And there should be 70 examples, and then the remaining 30 examples in our test set down below. So what we want to do is, what we want to train our model on the training set and then evaluate it on the test set. Okay, now let's implement our Perceptron model. So yes, the Perceptron code, let's type this one and then I'll get back to you. Now you can see it's relatively short. I'm implementing it using a forward and backward method. And why I'm doing this is because that is also how things are done in PyTorch, and it will make things more familiar later on if I start using this habit. But let's start at the top. So I'm implementing it as a class here, and you should be, I think, familiar with Python classes. So here what I'm doing is I'm running the constructor. So this is a special class method, a constructor. I'm giving it a number of features because that's what I need to know, the number of weights. And I'm using here the implementation where the weights and the bias are separate because that is more convenient. So I don't have to modify the feature vector. And what I'm doing here is I'm initializing the weight vector and the bias unit. The bias unit is just a single value, that's just one number, and the weight vector, it depends on the number of features, right? So I make this a row vector. So this is then equal to m, the number of features. So here I'm just setting up my weights and bias and setting them to 0. Later on, for certain algorithms, for stochastic uh, stochastic gradient descent, it's better to initialize them to small random numbers. Here for the perceptron, it's not necessary, but for neural networks it will be necessary later on. We will see that. Now in the forward method, I'm computing net inputs actually here in the linear, and then I'm computing the predictions. That's my threshold. So this is the net input. I'm calling it linear because later on we will also see linear layers in PyTorch. They are called linear, and they are basically computing net input. So this is you can see the dot product between the input vector and the weights, and then I'm adding the bias here. All right, then here we have our threshold function. This threshold function is just using NumPy. Here's how this works is, it's saying if linear, so if the net input is greater than 0, then output 1, otherwise output 0. So it's our forward method. And here is our backward method. In the backward method, why am I calling it like that? It is for computing the errors. So usually when we have deeper neural networks, we will use something called backpropagation, where we look at the outputs and then based on the outputs we adjust the inputs. So in that way we run the forward method to produce the predictions, and then we compute the errors and then update. So it will become more clear when we have a deeper network where there are really like a backpropagation going on. So these are our two methods. Backward is computing the errors, which is the difference between true class labels and the predictions, and forward is used to get the predictions in the first place. So we implemented here the prediction that's going on here that we discussed in slides also. Prediction is equal to step A, and then step B is the backward pass, which gives us the errors, and now we have to put everything together. So I implemented this train method here. So this train method is basically the whole thing here in the slide, as you can see. So for epoch, in the number of epochs, So this is for every training epoch, and then for every training example we perform the forward pass, the backward pass, and update. Since backward is already doing all forward, we just call backward here. There's some reshape here going on as well, and that is because we are making the vector dimensions match. Otherwise you will get some errors. So here this will be one row and m columns, so it will be, I think this is called a row vector, because this is just one and multiple columns, because it looks like a row. And here we have this row vector, and this has to have the same dimensions. I'm just making the same the same dimensions, so you can compute everything nicely. Otherwise you will find there will be dimension mismatch. So there's just a reshaping going on here, and then here we perform the update. So again I'm doing the reshape afterwards, so that we get the original dimensions back, because the weights here, see, we are matching the original dimensions. So we are just reshaping so we can add it to it. Otherwise there will also be a dimension mismatch if this is just a single number, or if there is 1 times m vector instead of m times 1 vector. And then also we update the bias. So the bias, it's just updating it by the errors. And then next thing is evaluating it. So evaluating the performance, here I'm just doing the forward pass and then compute the accuracy. The accuracy is computed by checking how many of the predictions match the true label, and then divide by the dataset size. So it will be giving me a number between 0 and 1. So this is my Perceptron algorithm, Perceptron class that we just implemented. And now I'm going to train it. So yeah, initializing it and then training it for 5 epochs, and then I will print the model parameters afterwards. You can see that it's pretty fast. So we get the weights, the weight vector, and then the bias here. And now we can evaluate it, like compute the accuracy. Let's do that. So the test set accuracy is 93%. It's not quite 100%. On the training set it should actually have 100%, right? Because it's linearly separable, this data set, and it should converge if it's linearly separable. And now everything is classified correctly. Test set is not as good, as you can see, because we may overfit. So let's take a look at the decision boundaries. Okay, so here is some complicated code to compute the decision boundaries. It's actually not that complicated. It's what I did is just rearrange things here. So what we have is, if you think about it, the decision boundary is greater or equal to 0, so everything hinges upon 0. So if we have our computations, it's x0 times w0, right, plus this, and put x1 times y1, then plus the bias. So this hinges upon 0. What we are doing here is we are taking one fixed number. So let's say we are taking for feature 0 the minus value of -2. So we are going to the left hand side here, and then we want to find so this is for x0. So x0 is the x-axis and x1 is the y-axis. So we take -2 here, and we want to find the corresponding x1 value. So this is x0 at -2. So this is what is the corresponding x1 value that we want to find. So we have to rearrange this, solving for x1, right? So what we do is we move this stuff and this to the right hand side. So we have x1 value here. So I get the x1 value. I'm calling it min. The reason is because it's the left hand side. Then I'm doing the same thing for the right hand side. So I'm doing it for the right hand side here. I'm again setting x0 to some value. I'm setting it to 2 here, and then I'm finding the corresponding y-axis value, which is the x1 max here. So I'm doing the same thing, just rearranging. Now I'm just using a max value, and then I'm connecting these lines, and that's how I get this. I've done this here for the left hand side for the training set and right hand side for the test set. So one is the training and one is the test set. Now about the decision boundary, it doesn't change actually, because it's the same for training and test set, just the data set is different because the decision boundary only depends on W, right? So we are providing these are fixed values, we are providing them, and the decision boundary only depends on the model parameters. So the decision boundary does not change here. So this is for the training set, and this is for the test set here on the right hand side. And you can see in the training set it perfectly classifies these examples, and on the right hand side this is just this is the test that you can see. It's maybe over fitting some of the data too closely. I mean, there's no other way actually, but it happens that here is this case, it doesn't perform well. In this case actually, there's a different way. If you would fit the boundary like this, something like this, more straight, then you may get these right, but it just happens that these data points are not in the training set, so the model doesn't know that it should shift boundary more to the right here. So in this way the model does actually a good job on the training set, but on the test set it's not so good. So in that way, it's actually, this term is called overfitting, because it fits the training data a little bit too closely and doesn't generalize so well on the test set. So this is how the NumPy code works. And now for the PyTorch code, I will not be writing this down, the complete code, because to be honest, everything is the same. Most of the things are same. I will only talk about the differences. So I don't need to talk about this much, I think, because the code is essentially the same. All things are same except for the class. Okay, so there are some differences though. Let's talk about only the differences. So I've prepared a slide for that, the differences that I feel we need to discuss. And also know that we will be talking about this in more detail when I talk about PyTorch code in the coming videos. So here I highlighted the differences. On the left hand side this is the NumPy implementation, and on the right hand side is the PyTorch implementation. So on the left hand side, this is the same code that we just wrote, and you can see that there are not that many differences. So the way the weights and biases are implemented here, we are using NumPy zeros here, we are using torch zeros here. We had a bit more, we should be a bit more specific. Instead of saying NumPy float, we say torch float 32. It's a 32-bit. I have this device here because of the way I implemented things that would also run on the GPU if there is a GPU available. If no GPU is available, it will use the CPU. So there's this device here which is provided optionally. It's not necessary though. And what's a little bit more is it's a little bit different. So here, I mean, there are multiple ways you can write that. You can also use a plus function. To be honest, I just happen to use torch.add, but I could have also used a plus. And then the is for matrix multiplication. In NumPy we usually write dot. In torch we write we write a PyTorch. We write like for matrix multiplication, but in PyTorch the dot function can also do matrix multiplication. So in a way it is kind of like the same thing. It just looks a little bit different. The where function in PyTorch is a bit more, I would say, involved. Not that much more involved, but it has to have placeholders, such as having a 1 and 0. It needs to have a tensor here. So I'm creating this as placeholders here and providing them, but it's the same concept. And then what's a little bit different here is the last part. So instead of numpy.sum, it's torch.sum. Here I'm converting it to the float, because otherwise it would be an integer, and then an integer divided by some value will give an integer. What we want to have is a float, because it's a fraction between 0 and 1. So if you don't do that, you will get back an integer, and that's not correct, because the value of accuracy is between 0 and 1, right? Which is why I'm casting this to float. But again, the PyTorch code will be covered in more detail later. So that is what I wanted to say about the code. If you have any questions, feel free to drop a comment. I hope you understood how to code this Perceptron algorithm using both NumPy and PyTorch.